also mentioned, they actually form the foundation stone of the analytics, right? Means all the conceptual part. So we will start with the most basic thing, right? And I will share the PPTs. After the session, the PPTs will be shared with you. So there is no problem of noting down everything, right? So all the PPTs, all the case data sets, and so on will be shared with you. Apart from the PPT, I may also use some additional material, so that will also be shared. So that won't be any problem. Related to the questions and answer, I will stop at a particular point of time and then I will take questions. So that would be better. Otherwise, it will be disturbing also, and sometimes a number of questions that are being asked will be taken care in the due course also, right? Like in when we progress the session. So I am sharing the screen, then we start the discussion. And one important part is there is no across the table concept here. We all are faculty members, right? We all have some knowledge, some information related to this. So either participants are faculty members, research scholars, or they have good experience in their domain. So we are at the same platform. So don't consider me the teacher only. Consider me a facilitator only, right? Okay, so I am sharing my screen and I will start with this part. Okay, one moment. So, right. So as the first topic that we are going to deal with, that is related to exploratory data analysis, right? So as it has been mentioned by Dr. Vinod Murthy, that everything is data, right? Means everything that we encounter is data. Data is actually the information. Right? So everything is to be converted into numbers or that information. So we start with the information, right? Or we can say we start with a thing that is known as raw data, right? Just like raw material, raw data contains every information, contains everything, but it is not directly useful. Since it is not directly useful, so we have to process this information, process this data to make it useful. So all these sessions are related to making the information useful. And obviously, these utility factors hold different connotations for different people. So it depends upon our domain, our expertise, our requirement. What do we consider as useful or utility? So, and every other thing, the software or all the technical part is just a facilitator to convert a raw data into a useful information. Whenever we obtain data, data may be in the structured format. Structured format means it would be in the form of some sheet which has some rows and some columns. Traditionally, we have variables in the column and cases in the row. Variables means all the fields, all the features.
Now you listen.
Ms. Sudha, kindly mute your mic. All the participants are requested to mute their mic, right? So the first one is the structured data. Structured data means that will be in some format. This format can be an XLS format. This format can be a CSV file. This format can be a SPSS file, or this format can be a Python file, right? It is a structured data. So normally the structured data is in the form of rows and columns. In columns, we have variables or the fields or the features. And in the rows, we have information from different unit of analysis or different respondent or different persons or units giving us information. Other type of data is unstructured data, which is primarily used in big data or in NLP or even in computer vision. So we have both type of information, structured and unstructured data. Since we are starting the FDP, So my part is primarily related to structured data. So I will start with the structured data. Later on, different speakers will take up unstructured data, and that would be converted into a structured data. So our structured data or any type of data may be broadly classified in between three categories. One is when we collect information at a particular point of time. So one-time information collection is known as cross-sectional data. Cross-sectional data means we have complete information related to a particular problem situation at a particular point of time. The second type of data is that data which is arranged as per the time element. So this is known as longitudinal data. And panel data is actually the combination of both when we arranged cross-sectional data with respect to different point of time. So this type of the data that we primarily encounter. The other categorization of the data is, remember, data means we have numericals, we have numbers, but it is not necessary that numbers are directly measuring something. So accordingly, we have a metric data and we also have non-metric data. Metric data simply means where the data is used for the measurement purpose or it represents a measurable thing. Other is non-metric data. Non-metric data can be categorical data when we develop some categories, or it can be ordinal also, right? What do we mean by categorical data? Suppose we take information related to gender. So one is male, other is female. We can assign 1 for the male, right? We can assign 2 for female. So here 1 and 2 are the numbers. They are the numerical information, but they are not measuring something, right? So they are not measurable. Ordinal means whenever we have ranked data, right? So these are the Dr. Richa, can you mute other participants? Okay, right. So we have two types of data. One is non-metric, other is metric. Metric means measurable. So accordingly, we consider 4 types of scales when we discuss this type of data. As I have mentioned, the first one is the nominal data or the categorical data, where we use categories or for the nomenclature purpose, right? Just like the example of using room number. Room number is, the numbers are there, but the objective is for the nomenclature purpose. In the same manner, suppose we buy a particular brand. So we can assign code 1 with the brand X, code 2 to the brand Y, and code 3 to the brand Z. So here 1, 2, 3 are just a categorical in nature. In the same manner, when we move to other category, the other one is the ordinal data, which is the rank data, right? Like we assign rank. So when we move from nominal to ordinal data, so it has 2 characteristics. One is there is an order, plus it also represents the name also. Yes, it is somewhat more powerful as compared to nominal data. These 2 data sets, nominal and ordinal, are primarily clubbed under non-metric data. They are clubbed under non-metric data. After that, we have 2 types of data. One is the interval scale data. Like in a number of situations, we use some scale. Like we can assign our students to different CGPAs. So CGPAs can be from 0 to 10, right? CGPA can be from 0 to 4, and so on. In the same manner, some very popular scales like Likert scale, semantic differential scales comes under interval scale, right? And after that, we have ratio scale. Ratio scale means the actual measurement. Right? Actual measurement means, Ms. Sudha, can you please mute yourself? Dr. Richa, can you mute Ms. Sudha?
Yes, sir. I'm doing that.
Okay, right. So after that, we have ratio scale. Ratio scale means the actual measurement, like the monetary value, right? Like the monetary value, height, right? So this is known as ratio scale. Both interval and ratio scale comes under the category of metric scale. The only difference between these two scales are, in interval scale, origin is not constant. Origin is not absolute. Means it depends upon our scale, that we can start from 0, we can start from 1, we can start from 10, right? Just like the temperature scale, right? In Celsius scale, origin is 0. In Fahrenheit scale, origin is 32. In Kelvin scale, origin is 273, right? So we will have an origin, but that origin may not be absolute. But when we go to the ratio scale belongs to that category which has absolute 0 as an origin. Means these scales always start with 0. So that's why they are the most powerful scale, because they represent the ratio property also. But as far as analytics or different statistical modeling concepts are there, both interval and ratio scales have equal importance. So we will treat interval and ratio scale as a scale part only when we consider the metric scale. So as we have discussed, as Dr. Murthy has also mentioned, what do we mean by data analysis or data analytics? Is to draw meaningful information from large part mass of the data. It is not an isolated activity. It depends upon all the steps that has been performed beforehand. So it is very much required that the data that we are going to process, that we are going to analyze, should be good on all this aspect. Otherwise, there is always a garbage out if the garbage in is there, right? So if we receive the wrong thing, then obviously we will have a wrong analysis also, or wrong meaning of wrong meaningful information derived from that analysis. So first, whenever we encounter a data, so this is, suppose this is our first encounter, first acquaintance with the data. So whenever we receive any data, we screen this data, right? It is exactly similar to the concept that whenever we meet a new person, then we try to screen that person, that whether that person is acceptable or not. Means we should start communicating with that person, or that person should not be accepted. This is very well expressed in all science fi movies. Whenever some extraterrestrial body or some robots or some machine comes to meet any human, the first thing that machine does is to screen that person, so that all relevant, all basic information should be derived. The same thing happens with the exploratory data analysis. Means we screen the data. This is also known as environmental reading. So the objective of exploratory data analysis is twofold. The first thing is we try to summarize the data. Right? Since this is a large mass of the data and we cannot draw any inference directly, so the first aspect is related to summarization of the data. So this is known as descriptive statistics. And we also examine our data, whether our data is a quality data or not. So this quality examination is also comes under exploratory data analysis. So these are the two objectives that we would discuss. First, I will explain the concept, then I will move to the analysis part or using the software. So as I have mentioned, that descriptive statistics, which is the first objective of any exploratory data analysis, is to summarize. Now, what do we mean by summarization? Since data is collected for some well-defined objective, since it is collected some well-defined objective or well-defined purpose, so there must be some similarity with respect to this data, because this data has been collected for a purpose only. Suppose we want to perform share analysis. So this data has been collected for an objective from a particular group only, from a particular unit only. Suppose we want to examine whether that person is eligible for loaning or not. So we will develop a model. So obviously we collect data for an objective. So there must be some similarity. So this similarity is known as center tendency. And we have different measures related to center tendency like mean, median. These two are the most popular tools. There is also one more method that is more, but it is used only for nominal data or categorical data, right? It is used only for nominal or categorical data, because in nominal or categorical data, we cannot measure anything. We cannot arrange anything. The only operation that is possible is count only. So that's why mode is used for nominal or categorical data. Traditionally, median is used for ordinal data, but in some particular situation, median can also be used for metric data also. And mean, as you know, is the most popular, most useful measure for metric data. We have some particular centiles also. Centiles are also known as positional averages, just like median. Means we can divide our data in 4 equal parts. They are known as quartile. If we divide our data in 10 equal parts, that is known as deciles. And if we divide our data in some order, so in 100 equal parts, that is known as percentiles, right? You must have heard about this term. This is very important. This is very useful term whenever we go for scores of participants in some competitive exams. So they will arrange the marks of those students in an increasing order. Apart from the similarity, we have one more concept that since data has not been generated from a column, from a thing that everything is same, so there must be some difference among people. So this is known as dissimilarity. So along with similarity, we have one more characteristic that is known as dissimilarity. And this is the dissimilarity because of which statistical modeling or machine learning tools or analytics comes in there. So if we don't have dissimilarity in the data, then there is no need for all these tools. So when we consider the dissimilarity, then the popular measures are range, which is the difference of maximum and minimum value, interquartile range, which is the difference of third quartile and the first quartile. Third quartile contains 75% of the observation, and the first quartile contains 25% of the observation. So interquartile range is actually the range of 50% of the middle information if data is arranged in some order. And these are the two popular measures, standard deviation and variance. Variance is simply the square of the standard deviation, which is simply the average square deviation from the mean. So the broad formula is this much. So as we know, this x minus x bar is the deviation from the mean. Square means this is the square deviation. And if we divide it by n, so it is simply means average or mean square deviation. Right? So it gives us the indication of variability present in the data. After that, we have two other measures. They are termed as shape of the distribution, whether our data is symmetric or not, or whether our data has a normal flatness or data is highly peaked or highly flat. And these are the various graphs and diagrams. These are the various visualization tools that are used to express the data. We are not taking up these tools separately. We will take up when we do with different part of the analysis. So far we have discussed the first part of the data, first part of the exploratory data analysis, which is related to summary statistics. The other part is data examination, which is also properly known as data wrangling or data munging. Why this part is there? The objective of this part is examining data before applying analytical technique. So we have gain insight through the data screening, means we have basic understanding of the data or the relationship. And the second part is related to the quality aspect, which means ensuring that data underlying the analysis meets all the requirements, right? So every data analytical tools requires certain requirements, certain assumptions. So we check whether these assumptions are there or not. So actually it works as investment in the data analysis technique. How it works as an investment? Because if we dedicate sufficient time at this step, then the future problems when we employ the different analytical tools won't be there. So this part is actually consists of data preparation. So in the data preparation, we adjust the data. If data is not of good quality, we purify the data after cleansing the data. So now we will discuss how we cleanse the data or how we purify the data. So as it has been mentioned, that different visualization tools can also be used using different graphical examination to profile the data. These are the different tools that are used for the profiling purpose. It is the univariate profiling, means all the variables, all the features are considered separately. But when we connect two or more than two, then that belongs to the bivariate profiling, and in the same manner, we go for the multivariate profiling. The objective of the bivariate profiling is either to explore relationship or to compare the data or compare the features, right? So these are the two objectives for which we use bivariate profiling. We will discuss in the due course. So these, since I am taking up the this part using SPSS, so these are the SPSS screenshots that you can use. So it will be helpful for you if you forget something. So at present, we are not discussing it because we would run the analysis directly, and all these things would be covered when we run the analysis. So now we are considering what do we mean by quality checking of the data. So in data quality checking, primarily we consider three aspects. The first one is we examine what is the volume and pattern of the missing data in our data set. The second one is whether our data has some very aberrant values, some very different values, like our data has some extreme values or some outliers present in the data. Right? I am not saying that it is a good thing or bad thing, but we should be very much aware that what is there in our data. And the last one is checking different assumptions in the data. Like we want to examine the most popular assumption to be checked is whether our data is following normality or not. So basically, in this session, we would consider these three aspects. We would examine the volume of the missing data. Next is whether our data is having some extreme values or outliers. And finally, whether some particular assumptions are being met or not. So as we discussed the first aspect, why missing data is important, right? Because missing data means when valid values on one or more variables or cases is not available. Means we cannot derive derive information on some particular variables or on some particular cases. Variables means the features that we are going to consider, and cases means the respondents or unit of analysis that is providing the data. So if our data is having large missing observation, it has an impact on the generalization of the result because it reduces the sample size that we are going to examine. And the main point of concern is twofold. The number one is what is the volume of the missing observation? if we have more than 10% of the missing observations, right, means the volume is quite high. The second is pattern and relationship of the missing data, means whether the data that is missing is random or it is following some particular pattern. If data is random, there is not much of the problem. But if missing data is showing some pattern, then it is very much required that we should identify the pattern that is inherent, that is generating the missing observation. So we are discussing related to volume of the missing and pattern. If data is scattered randomly, then there is no problem. But if there is non-random missing data, data is missing because of some pattern, because some of defined causes, then our results may be biased. So this is an important thing. So these points are discussed. And now the question arises, if our data is having substantial amount of the missing observation, then what can be done? So there are two approaches where we consider the present data. Means we don't go for any missing value treatment. We consider what we get. The first one is known as list-wise approach or complete case analysis. Here we consider only those cases where we have full information. Right? We consider only those cases where we have full information. Means we will delete all those cases where one or more than one variables or features are showing a missing data. Other is the pairwise approach, that is known as all available approach. It means suppose we want to examine feature 1 and feature 2 and data is missing in feature 3 and feature 4. So we will very well go with feature 1 and feature 2 data. Means we don't bother whether the missing data is there in some other feature or some other variable. So pairwise approach or all available approach, as the name suggests, uses all the available information whether they are present or not. But in complete case analysis or list-wise approach, we delete information from the entire case, even if one feature is showing us some missing data. So these two are approaches. It depends upon our analysis. Like when we go for some associative modeling or like regression modeling. So normally we prefer list-wise approach. But if we go for hypothesis testing, we can go for pairwise approach also. After that, we go for missing value treatment also. We replace the missing values by either mean, median, or linear trend, interpolation, and etc. This is known as missing value imputation. So normally we replace the missing observation using mean and median. So we replace those values by mean and median. But if our data is following some trend or our data is longitudinal in nature, normally we go for linear trend or interpolation method. So this is the imputation method where we try to replace the missing observation by some average values. Now, one very important thing arises. If we instruct the software, then obviously software will replace all the missing values by mean or median. But it is very important as a researcher, as an analyst, that decision should be taken whether to use imputation or not. Means imputation makes sense or not. Let me take an example. Suppose we have two data sets. In the first data set, 15% observations are missing. In the second data set, 60% information is missing. If we use imputation technique, then these 15% observation will be replaced either by mean or median of that variable. And if we use imputation in the second part, then all this information, all these 60% cases which are unavailable are replaced by mean or median. So the question arises, we should use imputation in both the cases or not. So can the participant suggest whether we should use imputation for both or we should not use imputation in a particular category? Yes, participants?
No. Sir, are you able to hear me, sir?
Imputation for 1. Yes. Okay. So, Mr. Ravi has mentioned that there should be imputation only for first, right? So, obviously, the question arises, why not in the second? Suppose we have used imputation in the second. So, 60% observation would be replaced by uh, some measure of central tendency by mean or median. Means, what characteristics would we lose? We use the dissimilarity characteristic of the data, because in this case 60% observations are exactly similar. So as we lose the dissimilarity characteristics of the data, then obviously we would be losing all the information which are derived from variance or dissimilarity. So it should be very important, right? Right. Non-reliable, right? This answer is correct, that non-reliable. Non-reliable means the dissimilarity aspect or the variability aspect of the data is being destroyed. And variability being a very important part of any data analysis. So we would, we should not use this method for the second one. After that, we go for the second aspect, that is known as examining outlier or extreme values. So outlier or extreme values are a part of the data, but they are distinctly different from others. Means they are standing out from others. So the question arises whether to retain or to be eliminated. And here a lot of discussion is required whether to retain that data or to eliminate the data. In some situation, retaining is useful, and in some situation, elimination is useful. So how can we detect that we have a presence of an outliers? So first, we compare the two important measures of central tendency, that is mean and median. So if there is not much of the difference, then we can say outliers are not there. But if there is much of the difference, then it indicates the presence of an outlier, because mean being dependent upon all the observation. So it is badly affected in presence of outlier or extreme values. But since median only consider the order, it does not consider the magnitude, though it is not a good thing, but in this manner, they are not much affected by outlier. So if there is a difference, major difference between mean and median, it simply indicates the presence of an outlier. After that, we can compare mean and 5% trimmed mean. What do we mean by trimmed mean? As we know, trimming is always performed on the edges. So what do we mean by 5% trimmed mean? So in 5% trimmed mean, 5% lower observation and 5% of the upper observations on the edges are being eliminated. So we consider only the 90% of the middle information, right? So if our data is having an outlier, so outlier might be on the lower side, on the extreme lower side, or on the extreme upper side. So outliers would be either on the belongs to the either 5% of the upper part or 5% of the lower part. So obviously, if we use 5% trimmed mean, then outlier would be eliminated. If our data does not contain outlier or extreme values, then there won't be any impact on mean. There won't be any impact on 5% trimmed mean. And in that case, mean and 5% trimmed mean comes out to be much similar. But if there happens to be major difference between mean and 5% trimmed mean, means outliers are there. After that, there is one more comparison, that we can compare mean with M estimators. M estimators are the robust estimators. Since they are estimated using MLE, so they are least affected by an outlier. So there would be minimum effect of outlier on M estimator. So if we compare mean and 5% trim mean, it means outliers may be there. We can also use the different statistical measures like Z-score. Z-score is simply we subtract each observation by the mean and divide it by standard deviation. So these are known as Z-scores. Normally software provides us the methods to calculate Z-score also. So these Z-scores are broadly greater than 3. So they indicate the presence of outlier or extreme values. In the same manner, when we run the spaces analysis, we can use box plot also. I would explain the box plot concept also, how we can identify outliers or extreme values. So let me discuss here also. So when we run the analysis, so that would be useful. The box plot is a very useful visualization tool. It consists of 2 boxes and 2 whiskers. These are the 2 whiskers and these 2 are the boxes. Here, this central part is known as, represents the median, right? Means the second quartile. This is known as first quartile, means below which we have 25% of the observation, right? So from Q1 to this edge, we have a difference of 1 interquartile range, right? So this is a difference of 1 interquartile range. Means broadly 25% of the observation comes in this whiskers. And the upper edge of the box represents the position of Q3, means 75% of the observations are below it. And on the upper side also, we have 1 quartile range. Quartile range is simply Q3 minus Q1, right? So this is 1 quartile and up to this part. So this is the broad shape of any box plot. So if any values goes beyond it, suppose we have a value beyond this range. Suppose a value lies in between 1 to 1.5 interquartile range, right? We have a value in this range, 1 to 1.5 interquartile range, or some value can be beyond 1.5 interquartile range. So if any value is in between 1 to 1.5 interquartile range, then this value is termed as outlier. And if any value of the data goes beyond that, means goes beyond 1.5 interquartile range, it is termed as extreme value. In the same manner, on the lower side also, if any value on the lower side lies in between 1 to 1.5 quartile range, it is termed as an outlier. And if value goes beyond 1.5 interquartile range, it is termed as extreme values. So we can differentiate between outliers and extreme values. They are mentioned here also. So these are the certain assumptions that we discussed. Now let me run the analysis and then I will go back to this case again and to this PPT again, and we will discuss. So there is a case, this case would be shared with you. This is the SPSS data file. Just to save time, I am not mentioning how the SPSS data file is being generated. It is available everywhere, right? So we are not giving time for the SPSS sheet generation. This case actually consists of a company that is known as Ventura. The case would be shared with you. This has 1150 outliers, 1150 outlets or 1150 sales representatives. And from those 1150 respondents or 1150 outlets, information is collected from 60 only. So we have a sample data. And this information is collected with respect to various aspects, like where the outlet is being situated. So the first is with respect to location, whether it is in the northern part of the country, it is in the eastern part of the country, whether it is in the western part of the country or in the southern part of the country. This is the first categorization of the outlet or the sales representative. The second is whether that outlet those sales executive, sales representatives belongs to the urban, cater to the urban area or the rural area. So one code is used to denote urban outlet and two for the rural outlets. So here, as you observe, for the location and type, we have used categorization. Means there are 4 categories for the location and there are 2 categories for the type. So the data type is nominal in nature. So here we have nominal scale type, nominal measurement. After that, we have 4 quarter sales. The first is sales of the outlet in the first quarter in thousands of rupees. The second variable is sales of the outlets in the second quarter. The next one is the sales of the outlet in the third quarter. Last week, sales of the outlet in the fourth quarter. Since here the values are collected on the ratio scale, they are represent the real measurement. So these are the scale variables. And since this is a toy case, this is a toy situation, it is used for the demonstration purpose. So it does not have missing observation. And this is the data view where the data is being presented in a file. This file has similar appearance just like Excel. On the column side, we have variables or the features like location, type, quarter 1 sale, quarter 2 sales, and so on. And on the row side, we have cases that represents the outlet number or the outlets which are chosen in the sample. And this represents our data. Right? Here, everything is numerical in nature, but these 2 variables, these 2 features represent the categorical data. After that, we have metric data. So hopefully this data set is clear to all. Or any question, I can take question at this point of time also. Any question?
Participants, if you have any question at this point of time, you can unmute yourself.
I'm a bit fast only, I mean, since we have to cover a lot. So, okay. Right. So first we are going to do exploratory data analysis. So if you have used SPSS, you must be familiar that all the analytical tools are available under the drop menu of Analyze. So from Analyze, we go to Descriptive. And I am directly using the most preferred option, that is Explore. So we have other options also, but they are elementary in nature like frequency and descriptive. So we are using the main option of Explore. We are using the Explore option. Just for the demonstration purpose, I am selecting 2 features, that is sales of the outlet in the first quarter and sales of the outlet in the second quarter. And they are entered into the dependent list. And since we are going for the analysis for the first time, so we are performing this analysis of the entire sample. But suppose you want to divide this analysis with respect to location or type, so you can enter location in the factor list. You can also enter location type in the factor list. So our output would be divided with respect to different location or with respect to different outlets. But for the time being, we are considering the entire sample as a whole. After that, we have a button known as statistics button. So in statistics button, we have certain commands. So descriptive is being checked in the default. We can also introduce M estimators or the robust estimator. So to check the presence of an outlier. And we have one more option of an outlier. Here, a simple outlier simply means in SPSS generates, SPSS gives top 5 and bottom 5 observation. Whether they are outlier or extreme value, it is not decided by SPSS. It only provides the top 5 and bottom 5 observations of each feature. So just to show you, I have checked outliers also. Then we have plots, right? In plots, we have box plot already checked. We have stem and leaf. Just to show you, though you are much familiar with the histogram, I have introduced histogram also. And in due course, we are examining normality of the data. So I have checked normality plots also. So these have been introduced, and I am moving to the main dialog box using continue. Everything is being there in the screenshot. So you won't have any problem in navigating from one window to other window or from one dialog box to another dialog box, right? So running the software is very simple and it is very well there in all the PPTs. So you won't have any problem. After that, we press OK. So here we have the output. Right. Here we have the output. So participants' outputs is visible to all of you. Output is visible to all of you.
Sir, it is visible.
Yes, sir. Yes, sir.
Yes, sir. Perfectly going.
Okay, thank you. Right. So here the first is case processing summary. So as you observe this table, here we have two types of N's. This is total N, and we also have valid N and missing. So this total is the sum of valid and missing observation. Since this is a toy case, so it does not have any missing observation, but in real life cases, we have missing observations also. So suppose 10 observations are missing. So we will have valid as 50 and missing as 10, right? So obviously 10 out of 60, right? So you can calculate the percentage. So here this table gives us the volume of missing observation. It does not tell us the pattern, but it tells us the volume of the missing observation. And it is for us to decide whether we should collect more information or we can use some imputational technique. So this is about the missing value treatment. And suppose your data is having missing values and you try to impute that missing values. Then you can go to transform. In transform, you have an option of replace missing value. So if we go to transform, then we have an option of replace missing value. We will select the appropriate variable, and here a new variable will be created. And this original variable won't be touched because always the original variable should be saved for any future analysis also. So here a new variable would be created, and in new variable, all the missing observation may be replaced by series mean, median, linear interpolation, or so on. So by this method, you can employ the missing value treatment. Anyway, we are not going that. Now we come to the second part of this table, that is the descriptive table. Okay. So in descriptive, if you observe this, the first part is the sales of the outlet in the first quarter and sales of the outlet in the second quarter. Suppose we want to compare sales of these two outlets. So, and suppose we are comparing mean. So average sale or the mean sale of the first quarter is 81.17 thousand and the average sale of the second quarter is 72.43 thousand. So if we compare 81 with 72, then obviously all of us would say that this company Ventura is performing good in the first quarter, but in the second quarter, there is substantial decrease of around 8.5 to 9,000 while moving from first quarter to the second quarter. This will be the general impression that we derive from the representative measure of the mean. Now the question arises whether this is a valid conclusion or not. So for that purpose, we have to consider some other features also, some other parameters also. Like in the first quarter, mean is 81.17 and median is 71.50. There is a major difference between mean and median. But when we move to the second quarter, the mean is 72 and median is 73. So not much of the difference, right? So there should be a warning bell that in the first quarter, there a large difference, large deviation is being observed in between mean and median. So we have to explore further. In the same manner, when we compare the values of mean with 5% trimmed mean, in the first quarter, there is a major difference around 9,000. But in the second quarter, there is not much of the difference. Mean and median both appears to be slightly means on the same side. In the same manner, if we go to the M estimators, as I have mentioned, M estimators are the robust estimators. They are estimated by using a maximum likelihood estimation. So they are least affected by presence of outlier or extreme value. So if we take up the M estimators of the first quarter, all these values are near about 72, right? In the first quarter also. In the second quarter, these values are around 72 or 73. So now if we compare mean with median, 5% trim mean and M estimator. So in the second quarter, there is not much of the difference. But in the first quarter, there appears to be much of the difference. So it should be a warning bell. Means there is something fishy in our data. Means our data may contain some outliers because the mean are badly affected by the outlier. So it means there is much of the difference. So by this method, we got an indication that our data contains an outlier. Remember, standard deviation or variance simply tells us the variability present in the data. They are not directly used to examine the presence of outlier or extreme values. So if there is a pattern in the data where the values are highly scattered, right? Like the first value is 90, suppose the first value is 54, second value is 154, next value is 254, next value is 350, next is 450. So obviously this data would contain, would have large standard deviation or large variance. But here we don't have any outliers. But if all the values are in between 54 to 100 and a single value is quite apart from all the other observation, so that simply reflects the presence of outlier or extreme values. So here we got an impression that our data contains an outlier. Now, since this software provides us top 5 and bottom 5 values, so if we take up the sales of the outlet in the first quarters, right? So in the first quarter, on the higher side, the highest value is 610. Then we have observations like 90, 88, 88, 87. So obviously we observe a large difference or the large gap between the highest value and the other values. So it is the indication of the presence of outlier or extreme value. On the lower side, we have values 54, 57, 57, 58, 58. Not much of the difference, right? So we can't say that there are outlier or extreme value, that this is perfectly okay data. In the same manner, when we go for the second quarter, we have highest value as 92 followed by 90, 89, 86, 86. Not much of the difference. Means again, our data neither contains outlier or extreme value. Now we've moved to the lower part of the second quartile data. Here the lowest value is 48. Next we have 56, 57, 58, 58. Now we have two points of concern. On the higher side of the first quarter data, highest value is 610. Then there's a large gap in between other values. In the same manner, when we go to the lower part of the second quarter, we have lowest information as 48 and 56. Right? So there is also a gap. But if we ask all the participants, probably none of the participants would say that 610 is a part of the data. Everyone would say that 610 is vastly different from other observation. But if we ask the participants of the workshop whether they consider 48 separated from 56, 57 and so on, or they consider this 48 not a part of the data, then probably there would be probably we would have two views. Some of you would say that consider 48 as a part of the data. Some would say that don't consider 48 as a part of the data. So values are different, but it actually gives us two concepts. One of the extreme value that I have discussed, and other is presence of an outlier. So let me let us consider these gaps, right? So here we are considering histogram. So here there is a large gap, much bigger the gap is. But when we consider the second quarter histogram, though there is a gap, but this gap is not much. Fine. In the same manner, if we consider the box plot, this is a box plot of the first quarter. So as you observe here, all the observations are in between 50 to 100, and there is only one observation that is situated at case number 55, and this value is above 600, right? And it is denoted by an star. So obviously this value is beyond 1.5 quartile range or interquartile range after this upper range. So this value should be termed as an extreme value. While we, if we go to the box plot of the second quarter, again there these are the observations. Majorly the observations are from 54, 55 going up to 90, 95, right? Because here the two boxes and two whiskers are there. But one observation is standing apart. This observation is situated at case number 48, and its value is less than 50, though we know this value is also 48, right? But here this value is being marked as a circle because it lies in the range of 1 to 1.5 interquartile range when we move from this lower range. So this should be termed as an outliers. Okay? So now I have introduced two concepts, extreme values and an outlier. Normally extreme values are considered to be the bad observation. So the recommendation is either get rid of that extreme value or we should modify that extreme value. But in outliers, it is discussion among data scientists, among statisticians, whether an outlier should be considered in the analysis or not. Some are highly recommender of including outlier in our analysis, right? Because it is actually the part of the data, but it is simply other from other observation. So in this case also, we will go with the outlier and try to modify the extreme value. Okay. So these are the outlier discussion. Now let me introduce one more participants. Kindly mute yourself. Some of you. Dr. Richa, you can mute.
Yes, sir. Can you check the name of that participant?
Dr. Sorry, M. Meenal. Okay, right. Now I'm introducing one more tool that appears. Okay. Suppose here, Miss Meenal. Okay. Here we have histogram. As all of us know that histogram is used for visual representation and for summarizing the data. But the drawback with the histogram is that though it summarizes the data, but it also removes the exact values of the data, right? Like if we have two set of observations, let me share the board again. Suppose we have two set of observations. In the first set, we have observations like 50, 51, 51, 51, right? So we have 5 observations in the range 50 to 60. So if we construct the histogram, so this bar would be from 50 to 60 and it has a frequency of 5 on. In the second set, we have observations like 58, 58, 58, 59, 59. So again, we have 5 observations in the range 50 to 60, 60 not included because it is an exclusive type. So again, if we develop histogram, right? So this corresponding bar would also have the length of 5 only. So if we have only the histogram in front of us, then we would got the impression that the first set and the second set are same, but actually they are not. But since this histogram compresses the real information, so we cannot figure out whether there is some difference or not. So for that purpose, I recommend a better representation that is known as stem and leaf diagram or stem and leaf graph. Actually, it consists of 2 parts. One is stem, then we have a dot, then we have leaf. So how this is constructed? So here the last digit would be put under leaf and all other digits are put under stem. Suppose we want to represent 56, right? So stem would be 5 and leaf would be 6. Suppose we want to represent 565, then stem would be 56 and leaf would be 5. In the same manner, suppose we want to represent 5665, then 566 would be the stem and 5 is the leaf. So if we use this diagram, so here the first can be represented as the first data set can be represented as 500111, right? So it will tell us that there are 5 observations and these observations are 50, 50, 51, 51 and 51. And the second data set can be represented as 88899, right? So by this method, we can also figure out that though both are having frequencies 5, right? But they are much different in nature. So by this method, stem and leaf can be built. So now I'm going back to the output where we have stem and leaf, right? So here we have stem and leaf. So it simply shows that there are 7 observations in the range 55 to 60, obviously 60 not included. And these observations are 56, 57, 58, 58, 58, 59, 59. So stem and leaf is used for the dual purpose. It serves the dual objective. It compresses the data, it represents the data, as well as it provides us the full information also. So in this manner, normally stem and leaf is preferred over histogram. So this is stem and leaf. So now you are much comfortable with the software and the analysis of outliers. After that, I am taking up the next part, which is related to examining the second part, that is the exam, mainly related to the assumptions of any analysis. And the most common assumption is our data should follow normal distribution. Right? Why it is so much important? Because some statistical techniques become invalid if it is not following normality. Right? Though there is a concept that if we have a large data set, then this normality can be compromised. Anyway, I am discussing how the normality can be checked. So by normality means all of us know normality basically represents that data has a visual representation of approximate bell-shaped curve. So if this is a bell-shaped curve starting from minimum going up to maximum, then this type of data, if this is approximately bell-shaped, then this type of data is said to be following normality or following normal distribution. So how can we check whether our data is following normality or not? First, we can compare the values of mean and median. If not much of the difference, then our data is following normal. Then we consider the skewness also. We can direct see the value of coefficient of skewness from the output. If this value is near to 0, then we can say that our data is normal in nature. In the same manner, standardized values can be used, right? It is simply the skewness coefficient divided by square root of 6 upon n, where n is the number of observations. If these values lies in between minus 1.96 to plus 1.96, then we can say that data can be treated as normal. In the same manner, kurtosis can also be used. These measures are available in the output. And there are different visualization plots, like the frequency curve or the histogram. Histogram also shows the bell-shaped curve. Stem and leaf, actually, if stem and leaf is a horizontal bell-shaped curve, then we can say that our distribution is normal in nature. Related to box plot, as I have constructed the box plot also. So if two whiskers are equal to each other and two boxes are equal to each other, then we can say that our data is approximately normal. And there is one more technique that is known as normal probability plots. So this normal probability plots is being constructed using observed values, observed frequencies on the x-axis, and expected normal means if distribution is following normal distribution on the y-axis. Right? Observed means that is observed from the data, observed from the data set, and expected means if they are normal. So if our data is normal in nature, then observed values and expected values would be same. Means if observed value is 10, then expected value would also be 10. Observed value is 100, expected value would also be 100. So if this is the situation, so most of the data points lie on this 45-degree line. So if most of the values are lying on this 45-degree line, then we can say that our data is following normal distribution. So now I am sharing the output to explain these things, right? So here, just like in the first quarter, we have major deviation, a major difference between mean and median. Skewness and kurtosis are much high, right? So normality is very much doubtful. In the same manner, if you consider normal probability plots, so as you see, the values are widely deviated from the 45-degree line. So normality is under doubt. But if we consider the second quarter, right? So if we consider the second quarter data, so here we have, this is the normal probability plots that I have mentioned, normal QQ plots or normal PP plots. We have observed value on the x-axis and expected normal on the y-axis. And this is the 45-degree line. Here, as you see, most of the points are lying on the 45-degree line. So overall, it represents that this distribution can be considered as normal. Here, there is a point, this is a point which is much deviated from the line. And this is the point which is situated as case number 48, which is having the value 48. So this is the position of an outlier, which is much deviated from the normal. The same thing you can observe here also in the first quarter. This is the first quarter normality plot. We have a much deviated point. This is a much deviated point from all the other points and much deviated from the normal 45-degree line. So it also shows the presence of an outlier. So this is related to normality plots. And these are the visualization tools. And we have some statistical tools also in the form of two testing of hypothesis tools. I will discuss testing of hypothesis in a detailed manner also. But for the time being, you can consider these two tests just to check whether our data is following normal or not. These two tests are Kolmogorov-Smirnov test and Shapiro-Wills test. Both tests are having the hypothesis as that our data is a good fit for normal distribution. Our data is normally distributed. So both are having tests. Both are having their own merits and demerits. They are mentioned in the notes also. And here we consider the probability values or the p-values. All the people who have from statistics background are much familiar with this value. For the other participants, normally p-values, I am taking a very practical approach to deal the p-values. They represent the probability of having such an extreme value, right? So suppose a p-value is 0.45, means there are 45% chances that this extreme value can be taken up. So obviously this 45% chances is not rare. It is a part of the population. So we do not reject our case, means we consider it as a part of the data. But suppose in some particular situation, suppose this p-value is 0.01, means there are 1% chances that such an extreme value would be taken in the distribution, taken in our case. Since this 1% is rare in nature, it is not that much common. So this should not be considered the part of the thing, part of the distribution that we are taking up. So if this is the case, then we would reject H0. Okay? Now, how can we differentiate whether this should be considered as a large value of P or this should be considered as a low value of P? So we, by the default manner, we take compare it with a particular value of level of significance, that is 5%. So this is just a default value. We can change this to 1%, we can change this to 10%, even we can change this to 20% also in some extreme cases. But in the default manner, we compare it with the 5% cases. So this is the most popular value. So if we compare the p-value with 5%, and the value comes out to be less than 5%. So less than 5% means we can consider it is a low value. So it represents the rare case. So if this is the case, then we would reject H0. Means we would consider it a small value. And if this p-value is greater than 0.05, then we cannot consider it as a low value. We consider it not so low, means not so rare, common value. So we do not reject in this case. So these are the broad categorization of discussion related to p-value. Okay. So if we go to the output part, and here we have these two tests. These are the tests of normality. The first one is a Kolmogorov-Smirnov test, and other is Shapiro-Wills test. So for the first quarter data, in both the cases, the p-values are 0.000, which is a very low value, which is a very small value. These values are less than 0.05. So we would reject H0, means normality cannot be assumed for the first quarter sales. While in the second case, for Kolmogorov-Smirnov, the p-value is 0.20, 20%. In the second case, the p-value is 0.489, that is a 48%. So in both the cases, these values are not so low. These values are big. These values are large as we compared with 5%. So we cannot reject the null hypothesis, and we can say that our distribution is following normal distribution. Okay. So these are the normality discussion. And there is one more important thing that should be kept in mind. Here I have mentioned also that normality is not a big issue. We can always increase the sample size. So if sample is of a large size, sample is of a huge size, then departure from the normality can be compromised. There won't be such of the problem. Otherwise, we can go for some transformations, like we can go for square root transformation, we can go for log transformation, or natural log transformation. So to convert non-normal data to a normal data. So this is all about this discussion. Any question up to this point? This is related to the various aspects of the data. Any question up to this point?
Participants, if you have any question at this point, you can unmute yourself. And if it is visible, please put on your camera.
So good afternoon, Dr. Kumar. Yeah.
Yes, Mr.
Ask a question. Yes, it's a very excellent lecture, sir. It's very informative. All the methods what you have explained are good. I have come across one more method how to form the normality of the distribution. Say the skewness divided by its standard error. If it lies between plus or minus 1.96, it can be deemed as approximately normally distributed. Is it correct?
That is mentioned in the notes also, right? We can consider the absolute value as well as Z value. So when we consider the Z value, it includes the standard error part also.
Yes. Nice, sir. Nice. I would like to clarify.
Any other questions?
No, sir. That's all.
Okay. Thank you. So, so far we have discussed the broad data introduction and the normality checking. Since I have to take the session or introduce the statistical inference part also. So I am starting the second part, that is the statistical inference. So now why statistical inference is very important. So whenever we came across data, even in analytics, we have two objectives. Number one, we go for some prediction purpose, and other is some explanation part also. Means that things are happening, so why things are happening. So when we consider the explanation part or why the things are happening, then this statistical inference becomes very important, right? If we go only for the prediction purpose, then obviously we are concerned with the prediction error only. Means we try to devise those models which have less prediction error. So we have twin objectives in an industry where prediction is more important, but they are also interested to know what are the reasons. But as a researcher, along with the prediction, we are also interested with the explanation part also, why things are happening. And whenever we get the data, how used the data is. Data is always from sample only, right? Because even if we have a huge data set, whatever we perform analysis, it will be applicable for some future data. So even for the big data set also, since the implications or implementation is on the future set also. So for the future set, it becomes a sample observation. So we are very much interested to know what is happening, what is there in the sample would be there in the population or not. So accordingly, we have a concept of statistical inference. So I am sharing the second set of slides. So hopefully slides are visible to all of you.
Sir,
yes, Dr. Risha.
We have another session at 3 o'clock. Can we?
But from 3 we have session on predictive.
Okay, sir. Because participants are also asking for the break.
So we can take, but what do you think? If we take break, because the first session, our session started at 15 minutes.
Yes. So
behind
you can, yes, sir, you can go for 15 minutes.
Right. So from
we can have 15 minutes. Yeah.
But otherwise, that session would be extended to beyond 4:30. So whatever your choice is, right? So should I take?
I think you can proceed for next 15 minutes.
I will give only the broad overview. Of the statistical inference, right? Slides are there. You can use the slides.
Okay. Yeah. Okay, sir.
So this is only the high-level introduction of the statistical inference, right? All the details are there in the slides that will be shared with you. So you won't have any problem related to various things. Otherwise, you have my number, my email ID also, you can discuss also. So the first part is related to conceptualization. Actually, whenever we go for some data analysis or data analytics, we have data from sample only. And we want to draw inference on the population. So this statistical inference is actually means inferring about the population on the basis of sample only. So why this is required? Because though we say that sample is a representative subset of the population, but representative subset never means that it is a perfect replica of the population. It can never be a perfect replica of the population. Moreover, from population, we can have a number of samples, right? We can have number of samples like n to the power n or capital NCN samples are possible. Since we have a large number of sample possible, so different samples may give different results also. So it is very much required to discuss whether the results that are derived from the sample would be there in the population or not. So this concept is known as statistical inference. Statistical inference actually consists of two parts. The first part is estimation, where we use a value from the sample just to represent, just to estimate that of population. So this is known as estimation. Other is since whenever we perform some analysis, either for the research papers or for some business perspective, we must have certain perception, certain claim, certain assertion, and we try to check whether this assertion is correct or not. Right? Obviously, this assertion is made for the population only. So if we have the population data, then there is no need of studying these concepts. But we never have data from the population. We have data from the sample. So we want to check whether our sample data gives us any lead, any indication of the correctness of these assertions about the population. This concept is known as hypothesis. Remember, hypothesis is not an assumption. Hypothesis is a positive declaration, is an assertion. So for the positive declaration, there must be something before this analysis, like there must be some exploratory study. Then only the hypothesis makes sense. So this exploratory study may be in the form of research papers. If we go for the academic research, it may be from some research report, or it may be from some experience survey, or it happens in past also. So there must be something before the analysis starts. So this is known as hypothesis, right? And we try to examine whether there exists a significant difference between the population values and sample values. And for that purpose, we use the method known as testing of hypothesis. So statistical, as it has been mentioned, the significance testing means we test whether there is a significant difference between the sample results and the population results. And it means significant testing, the concept part. So actually the significance testing is the concept part. It is just the concept part, and testing of hypothesis is the implementation of this concept. So I always consider this title better to represent the concept, means the significance testing. So how this is achieved? Here we construct two hypotheses. One is the null hypothesis, which is tested, which assumes no difference. And the second one is the opposite to the null hypothesis. You can observe the binary symbols 0 and 1, and 1 is opposite to not, right? So this is known as alternative hypothesis. Right? So this is the testing procedure. This is a broad testing procedure that we employ in various analysis. First, as per the situations, we develop the hypothesis. We develop two hypotheses, H0 and H1. After that, we define the set, define our test or test statistics. right? Means we make a rule that governs us whether to reject or not to reject the null hypothesis, right? This concept we will discuss in the later on. And after that, since we are going to use a sample data, so there is a concept of sampling distribution, right? What do we mean by sampling distribution? Because the statistics that we taken up from the sample, right, would be a random variable. Why it is a random variable? Because it can assume different values for the different samples. So we can never judge the real value, the exact value. Since this is a random variable, so it follow a probability function. And this probability function is known as, since it is the probability function of sampling distribution, so this is sample statistics, so this is known as sampling distribution. So we define the sampling distribution. Then we decide the criteria for acceptance or rejection. Since we are using only the software part, so I am not going into detail, and I am considering only the concept of the p-value only, right? So as I have discussed the p-value, and here we are taking 5% as level of significance or the default value for the comparison. So if p-value is less than 0.05, we reject S naught at 5%. Otherwise, we won't reject the hypothesis. Now, I will introduce certain tests related to these concepts. So let me share the whiteboard. One moment. Okay. So as per the data set, suppose we want to examine 3 scenarios. The first scenario is there is a claim that the average sale of the first quarter is, the first claim is there is an average sale of first quarter is 75,000, right? And some decision makers are not convinced with this claim. They want to examine. Remember, this claim is on the population, and in the population we have 1150 outlets in the Ventura, but we have data from only 60 outlets, right? If we have complete data set, then there won't be any necessity for this concept. So this is the first claim, that average sale of the first quarter is 75,000. This is the first claim. The second claim is, there is a claim that rural outlets are giving higher sales, better performance as compared to urban outlets, right? This is the second claim that needs to be examined. Now we have third claim, right? When we go through the case, then in the case it has been mentioned that at the beginning of the second quarter, an advertisement campaign has been launched, right? So obviously the purpose of the advertisement campaign is to increase the sale, is to augment the sale. So we want to examine whether the advertisement campaign is a success or not. It's a success or not. And we are considering only the immediate effect. Means it has been claimed that the advertisement, it has been claimed that the advertisement would have an immediate impact on the sale, right? And since it is launched in the beginning of the second quarter, so we want to examine whether the second quarter sales are greater than the first quarter sales, right? Right? So if this is the case, then we can think that this advertisement can be a success. Remember, we have data from the sample only. So this is the third situation. Now we have one more situation, that is the fourth situation. As you have observed that we have 4 regions. We have data from the 4 regions, that are the northern region, eastern region, western region, and the southern region. And there is a perception that sales or performance of the outlets are same across all outlets. Right? Means broadly we are considering then northern outlets are giving equal sales as compared to eastern outlets, as compared to western outlets, as compared to southern outlets. Fine. So these perceptions are on the sales only, right? And as we know, sales is metric in nature. And suppose we are considering mean, right? Though I know there is an extreme value in the first quarter, but suppose that extreme value, since we have identified that there is an extreme value, so that can be taken care of. So we have these four situations. And remember, we have only sample from at our disposal. So if we consider the first case, then we actually require only one sample, right? We take a sample of the outlets, and from that we have a sample value. So here we require one sample. In this case, we require two samples, because here we are comparing. Here we are comparison, and this comparison is in between rural outlets and an urban outlet. So we must have a sample representation from the rural outlets as well as sample representation from the urban outlets. Here also we are having two samples. Why two samples are there? Because again there is a comparison of quarter 1 sale and quarter 2 sale. So we have sample for quarter 2 data and sample for the quarter 1 data, right? And here in the last case, since the number of samples are more than 2, so we denote it by K samples. It is denoted by, suppose it is denoted by K samples. We have K samples. Fine. And since here the mean are using, so this is known as one sample testing of mean. Testing of mean. Here we have two sample comparison of mean, because we have two sample. Here also this is known as two sample comparison of mean, and this is known as K sample comparison of mean. Now we go to the second and the third part. In the second and third part, we are having two samples. So number of samples are same in both the cases, right? But if we consider this case, then urban and rural outlets are independent of each other. So in the very rudimentary language, we can say that number of units belonging to the rural outlets may not belong to the urban outlet. These type of samples are known as independent samples. Fine. But when we compare the outlets, so suppose we have two outlets, 1 and 2 and 3. Suppose we have 3 outlets and we want to compare these outlets with respect to the impact of advertisement. Suppose first outlet is a roadside outlet. Second outlet is situated in a remote area. And the third outlet is situated in a locality. Right? So obviously, if we want to compare the sales of the outlet, then only the first outlet sales should be compared with respect to Q1 and Q2 with respect to each other. In the same manner, Q1 and Q2 sales for the second outlet should be compared with each other. In the same manner, in the third case, they should be compared with the third only. It means this case should not be considered. Sorry. Means this case, right? This is the case. This case should not be considered with this case because they have external factors only. So in this case, if we compare, then we compare this type of situation. And this is also known as A/B analysis or A/B testing or paired test. They are also known as paired test. So here the samples are paired in nature. And here again, these samples are more than 2 and they are independent in nature. Right? So accordingly, we have different type of tests. if our data is following normal distribution, if normality is ensured, right, then here we recommend one sample t-test. Here we have two independent sample t-tests. In this case, since samples are dependent or paired in nature, so here we have a paired t-test, and here we have a k-sample mean test, which is popularly known as ANOVA. Right. So here the test is being used is ANOVA. The full form of ANOVA is analysis of variance. So kindly remember that here we perform analysis on the division of the variance, but it is actually test of mean only. So this is the case when we consider when the data is following normal distribution. Suppose our data is not following normal distribution, right? Then we cannot go with these tests. And these type of tests are better known as, if you know, probably, they are better known as parametric tests because they require the assumptions related to the parameter. The other type of those tests where we cannot make any assumptions about the distribution, population distribution, means the broad assumption, that is the normal assumption, cannot be made. So they belong to the second category of tests. They are known as when non-normality is there, when normality cannot be assumed. So they are better known as non-parametric tests. So we have non-parametric test also. Here we have equivalent test also, like we have a non-parametric one sample test like run test. Here we have two independent sample tests, that is known as, let me change the color. This test is known as two independent sample test or Mann-Whitney test. Okay. Here, since t-test cannot be employed and our sample is paired in nature, so we can go for sign test or we can Wilcoxon test also is there. We can go for sign test or Wilcoxon U test. And in the last case, if normality assumption is not there, then ANOVA cannot be employed. Then we have a test known as Ruskell-Wallace test. We have a Ruskell-Wallace test. So parallel tests are there. So the objective of telling about this test is simply that we have an option for everyone. So that's why the assumptions checking is very much important. In principle, parametric tests are supposed to be more powerful. They have better discrimination power. They have better accuracy as compared to non-parametric tests. But we also know that if we increase the sample size or sample is of huge size, then it is immaterial whether we are using parametric test or non-parametric test. Okay. So since 215 is there, so I am stopping here. We can have a quick lunch, right?
Sir, thank you for the session, and I think you have touched all. If you have raw data in your hand, how can you handle the data? How can you check the missing value?
That I will take, Dr. Disha, that I will take after this class. Right?
But you have given the conceptual clarity about all the basic thing, about all the exploratory data analysis, and further once you have explored your data, once you have visualized your data, how can you go for the further inference?
Pardon, Dr. Disha, there is a question from Mr. Ravi Kumar. This question is related to one tail or two tail.
Yeah,
it is actually related to our critical region. Like if we want to compare if the values are increased or decreased, right? Means in that case, we will either have greater than or less than. So in that concept is known as one tail test. But if we are simply comparing and we don't have any directional indication, means whether the values are same or different. So different can be greater than or different can be less also. So in that case, both the tails are involved. So the critical region lies on the both the tails. So those type of tests are known as two-tail tests. I will explain when I run the analysis.
Yeah.
Okay, thank you.
Thank you, participants. I'm again going to share the link for the attendance. Okay, if you haven't marked your attendance, please mark your attendance, and we will start next session by 3:15.
Okay,
thank you,
so
sir.
3:15, right?
Yeah,
all these PPTs would be shared.
Yeah.
Right? Don't worry.
And also, sir, please keep on saving whatever you are writing on the PPTs.
Okay, right. And the data set will also be shared. Don't worry.
Okay.
Okay, thank you.
Thank you, sir. Thank you so much.
Thank you, sir. Thank you.
So I have shared the link again. So if you have missed your attendance, please mark this. Okay, it will be there for 5 minutes, next 5 minutes. Another participant, you can sign out and you can again log in by 3:15.